Well, Frank is a research geophysicist at the Institute for Geophysics and Planetary Physics here at Scripps Institution of Oceanography. He's a longtime San Diegan, and he received his BS in physics from UCSD and his PhD in geophysics also from here at Scripps Institution of Oceanography. So you've been here quite a while, Frank.
Can't get rid of me yet.
I hope not. We want you to be here a long time. Frank started the local ANZA seismic network in 1982 and has been a key partner in seismic station installations all over the globe. And we will be having a screen here where you can actually interact with the seismic, the ANZA network and see what's happening at the ANZA stations. Frank's primary research interests are in the area of earthquake seismology, real-time data acquisition systems. In fact, some of you may have seen the talk he gave about 2 years ago on the RoadNet project. And there's also, he's very interested in time series analysis. Most recently, Frank has joined an ambitious NSF-funded initiative called US Array. And that US Array is a transportable array of at least 400 portable unmanned seismometers. And they're displayed on a uniform grid, and they're going to systematically cover the whole of the US so that we're going to get a lot more very exciting and important, interesting seismic data that way. So tonight, Frank is going to speak to us on earthquakes, seismic science in Southern California. Thank you very much.
Thank you very much. Instead of talking about US Array and some of these other global systems we're talking about, that Nigella was telling about some of our other research projects, I'm going to talk to you today about earthquakes and earthquake hazards and earthquake early warning, possible earthquake early warning systems that we can apply in Southern California. As with any presentation here, this is not the work of one person. This is I'm going to be drawing heavily on the work of Bridget Smith, Debbie Kill, Jennifer Akins, Atul Nayak, Rob Newman, Jennifer Matthews, and the whole rest of the ANZA group, which basically runs, operates all these stations and equipment that we show and produce data from. So today I wanted to go over some of the issues like what do we know about earthquakes in California? Why do we make the assumptions that we make, and what are the things that we might expect in the future? And what are the projections looking backward in time, what would might have happened based on various sets of data? Also, from there, I'll go to some of the ways we actually make measurements of earthquakes, because the instruments that we deploy and actually send data back to here and show. And then I'll talk to you a little bit about the wide area wireless networking and some of the opportunities that the new and evolving technologies are presenting to us that we were never able to do before, particularly when we thought about doing the ANZA networks in 1982. And which is one of the specific cases talking about earthquake early warning systems. And then I'm going to show some models and some modeling results based on what we know of seismology and how that might mean to us as Southern Californians, and how we might go, what we might expect to see in the future. So most of you, I'm sure, are aware that we can expect some serious shaking here in Southern California at some point in time. This is a map of Southern California with the potential for strong acceleration over the next 30 years, heavily focused by the mountains of where the San Andreas Fault runs, but we'll expect to see some high ground accelerations out here all the way down to San Diego and the Coachella Valley, up and along the Santa Barbara and so forth. So this is the kind of thing that we see all the time presented on like why we are really interested in earthquakes in California. But the real question is, how do we get to this information? Why do we make a map such as it shows? So what do we really know about earthquakes in California? Here's a map made of the San Andreas historical earthquakes from beyond San Francisco all the way down to the Mexican border here. As you can see, there's lots of earthquakes. It's color-coded by time. And there's kind of two dominant earthquakes. One is the San Francisco earthquake up here in 1906, and the other one is the 1857 Tejon Pass earthquake, which is like kind of the largest one in Southern California. And say lots of other smaller earthquakes that have occurred at various sites in between over the years. So all these things that events that are shown on this map have all been felt strongly, and so they are definitely written into the historical record. These are not ones that you would have to use a seismograph to read. You read a newspaper to figure these out. A little bit more detail on how these things work is like this is, I'm scoping in here to Southern California, in particular, sign of why we are focusing our work on, and where we work in Southern California. But you notice on the last map, there's a lot more earthquakes that I'm showing here with bars on it. Now we just see these tracks, railroad tracks here that show actual surface ruptures. So all those other earthquakes shown here by the circles actually didn't rupture the surface. So these are the earthquakes, these are the big earthquakes that actually had surface rupture that you could walk to and say, okay, there's that road, it went a meter to the right or 2 meters to the right. You can actually walk up and see it. All these other earthquakes are felt, but they didn't actually rupture the surface, or there's no known surface observation of it, depending on how old it is. So what that's telling you is that, you know, what we see on the surface is only a lower bound for the number of earthquakes that you might see in the region. You can actually have more large earthquakes. I mean, you look at the Loma Prieta earthquake up in 1989, I mean, that was magnitude 7 earthquake that didn't break to the surface. You know, that's actually fairly significant. That gets your attention. So one of the places that we look at for information and how we estimate what's occurred over time history is we look at things what's called paleoseismology. And this is a study done by geologists who actually dig holes. They come along to a place on the fault. This is the San Jacinto Fault that we're looking at right here in a place called Hog Lake up near the town of Anza, California. And the fault runs right through this region here, and then there's a little, they find a little step over here, and they just get a big backhoe out there and dig a big trench. Well, inside the trench, they look at all these gnarled versions of strata, and they start mapping out these little details and where the fault broke through to this point, and it's covered by this strata and all these sort of things. And through technology such as this, you can actually date earthquakes prior to the time when people settled in this region. I mean, one of the problems we have in Southern California is that we just haven't had a population that goes beyond about 1900. You get back to an earthquake that was measured in 1890, there is no place that you can say that there's people. You know, it's felt over a wide area, but there's only 3 or 4 reports, and it's along a railroad track that ran from LA all the way out to the Arizona border. That doesn't help you much on location. That doesn't tell you whether it's Riverside County, Imperial County, San Diego County. So that's one of the problems that we face when we go further back in time, trying to date these things and find out where the big earthquakes are going to occur. But in this place where we actually know where there's a seismic fault, and we can actually go dig these trenches across here, and this is work done by Tom Rockwell out at San Diego State, you can actually go back and look back here. Okay, we can see by measuring these, where these surface faults break off and where they're covered over and dating these strata in the geological column here, you can see, okay, in Anza, this particular area, which is a place of high risk, and if it actually ever breaks again, which it will, we're going to really feel it here in San Diego. But the previous earthquake is 1760, and it's the most expected date based on the dating, the radioactive dating that they used. The one prior to that was 1630. Well, you know, if you can do the math, it's 130 years between those two good-sized earthquakes, isn't it? And you go back further, and you got, okay, it's from 1360, so that's, you know, 260 years, 270 years. And then it's a short term to, a short jump back of about, 70 years, and then back to another 60 years, and a big jump about 230 years. Well, what do you see in that picture that will get your attention here? Where's today? I'm getting a little concerned about that one. So when you look at Southern California and look at the faulting systems here, this is the way that we look at things, where you look at places where we know there's been surface rupture and where there's been big earthquakes over the past, the past 100 or so years. 1857 is a well-known earthquake because it broke basically from here, which is in San Bernardino, up near Cajon Pass, where the 15 highway goes through. It broke down to about there, went all the way up to Paso Robles. So that's a well-known earthquake. I mean, that one we can pin very, very directly. But we get south of there, we look at the Hector Mine, which is out here in the Landers earthquake. We have the 1918 earthquake, which is here on the San Jacinto Fault. But there's two areas out here that we really haven't had much. One is this offset of the San Andreas Fault on the far side of the Salton Sea, the southern segment, and the other one is this section on San Jacinto where that Hog Lake section I showed you for the paleoseismic work was from. So that comes down, and so we're not that far away. It's only 60 miles away. Out here it's about 100 miles away, and we could have a much bigger earthquake out here on the San Andreas based on what we know about how the plates are moving and what the expected slip rate along the San Andreas is. And I'll show you some more examples of this later, why we expect this. But suffice it to say that if this thing broke, and the last known earthquake out here is about 1600, 1650 on this part of the fault, we're going to have a 6-meter offset. So that's going to, set off the interstate 10 quite a bit. You're going to be going on the westbound lanes and in the eastbound lanes if you're not careful, sort of thing. So, and only in here, this is a little short one. There's only like 3 meters of offset, so that's only it's kind of a magnitude 7 plus that if that one breaks all in one go. So as when I started this work actually as a PhD student here at Scripps, and my thesis advisor was very interested in this area, and he knew about that gap that we just talked about. So we installed this network in this region here, and there's a more detailed study. There's a couple faults in here, and what you notice in the seismicity with these black dots here are actually small earthquakes that occur in the region. But there's not only that, there's a hole in the big earthquakes that, there's nothing big that's ruptured through here, but there's lots of little earthquakes that don't even occur in here. So this is an area, very intense study of why this area is so locked. And we have had, magnitude 5 earthquakes right in here, and we've had some magnitude 4s up in here, but we haven't had anything of any significant size on that one center section. It's about 6-10 miles long in there during this whole period that we've been making measurements in there. So this is something that we really want to look at. Oh, and by the way, Hog Lake, right there in that gap where there's nothing there. So it evidently only breaks when there's big earthquakes. So that's the supposition that we're working on at this point in time. So the ANZA seismic network started out, we put in 10 stations up here in 1982. We have since expanded well out to the coast and started to take over San Clemente Island, invade out there too, and the Navy lets us. And make measurements all in here because obviously for an urban area like San Diego, we have major faults here in the San Andreas, we have major faults here in the San Jacinto, we have this Elsinore fault zone, Imperial Fault. We also have Rose Canyon Fault running right through, you can go out on the balcony there and see that one. And then you can see the San Clemente Fault out here, which you can measure, which you can see in the bathymetry, and you can also measure earthquakes on. So in 20 years, we've recorded something like 40,000 earthquakes in this region. Now, they were not scaled by size. Each one of these, almost all of these were not felt by anybody, but this gives you an idea of what the seismic activity is through this whole region in 20-year span. Now, it's sort of dominated, and the San Jacinto Fault turns out it's the most active kind of general small earthquake fault in Southern California. So it has earthquakes popping up all the time, heavily concentrated on the two ends of the fault. As I was pointing out, that gap is buried under the stations there, but that's actually where it is. But you also see other features in here. You also see the southern section of San Andreas out there. Do you see any earthquakes out there? Neither do we. There's lots of little ones, not very many little ones occurring out on this section of fault out here. But you see this big structure right here. This is the 1992 Landers earthquake, the aftershocks for that earthquake, which if you were here in 1992 in June, you felt it. June 28th, about 4 o'clock in the morning, probably woke you up. It certainly did me. It's one of those things as a seismologist you don't really like to feel as your bed shaking in the morning, It's a bad day at the office. And then you get, in 1999, you get up to the Hector Mine earthquake. Also, these are aftershocks of the Big Bear earthquake, which is associated with the Joshua Tree Landers sequence in here. So these sets of earthquakes are heavily dominated by a main shock and aftershock. And these earthquakes here are kind of background natural seismicity, which have been fairly constant over the whole 20 years that we've been monitoring this area closely. So how do we get data back here? What is it? We out in the field, so you have a seismic station out here in this concrete vault out here. And then you got this big antenna here with a little radio antenna up here, which is just standard, what we're using now. We started out using old license band analog radios, and now we're using digital spread spectrum bands, same thing, that's the same frequencies that you use for your cell phones, or not your cell phones, but your phones in your house, your portable phones that you walk around the house in. Well, it's the same type bands that we're using here. We toss the data up a cable here and throw it over to this mountaintop where it's received up here on Toro Peak. And so this is a central telemetry site, and as you might guess, this mountaintop has got lots of antennas on it because it's got one of the best views in all of Southern California. So if you ever have the opportunity to hike up there, I would highly recommend it on a clear day, because literally you can see the coast out, see the oceans and islands offshore out on this direction. That's Santiago Peak right there. And you see Palomar Mountain a little bit off to the left, as well as you can look into Nevada, Arizona, and Mexico from the same place. It's not very many places in California that you have that kind of view. So here's another view of Toro Peak, and say the facility's a little bit closer in. This is the antenna that we send data back to UCSD on. It's a small 8-foot dish, only about this tall, right? There's a little thing we had to haul up there. And then this is a view. We have one of the seismic stations out here on Pinyon Flat, one of the most geophysically instrumented areas on the planet. That's all run by UCSD and Scripps. And some other areas here give you an idea. This is Salton Sea looking down to the southeast, sort of down towards the Coachella or Imperial Valleys there. So from Toro Peak, which is up here, you can see the star pattern of all these little telemetry links of all we bringing data in from all these different stations, seismic stations, and are dominated on this side. We have a lot of GPS measurements, of real-time GPS measurements made by the Yehuda Box group, which is also at IGPP, bringing data in here. And then we build ourselves basically an internet all the way up to Toro Peak. That's what the red lines are and the white lines. So the difference between the red lines and the white lines are basically, one goes on a licensed spectrum that you have to pay the FCC to use. The red lines are free spectrum that anyone can use. And so we just basically send data up all these different ways, bring it back down. But it basically says, okay, I can put a computer on here and basically talk to a computer here at UCSD, or I can sit in my home instead of having to get up and drive into the office like I did in 1992 at 4 o'clock in the morning. I can get up and go log into my RoadNet account my Roadrunner account and pull it up. And there it is. I can see what's going on and make a decision on what we have to do if there's some event of interest. So it's really enabled us to do a lot of things which we were not able to do before. And the other thing is we're able to do now is start connecting lots of other sensors into lots of other places to start putting things in on portable deployments. Like if there's an earthquake on the Borrego Valley in here, we'll be able to set up a lot more instruments to do very detailed studies and tie it right in with the continuous real-time systems that we run and Caltech runs. So this gives an idea of what it takes to really do that sort of thing. I mean, lines on a map are one thing, or on a photograph, but you're talking some big iron when you're putting these antennas up on top of these hills. This is a Palomar Observatory that we have connected up so they could bring in data from their astronomical telescopes up there. And there's various different, and then it brings all the way back to the San Diego supercomputer through these various links here. But what we really care about is, like we're looking at out in the desert out here, we're able to access, this is an example of something we could, by putting in the internet capability all the way out to the mountaintops, all of a sudden, here's a station out here on Borrego Valley, which is run by the University of California, Santa Barbara. And they do some seismic measurements. They're looking at how the whole response of that basin is out in the Borrego Valley. An earthquake comes in, they want to shake it. And it was originally funded to look at nuclear power plant safety issues, like what happens if you put a power plant in a basin sort of thing. Well, if an earthquake comes underneath it, you want to see how much it amplifies, how much the ground shakes and things like that. Well, Santa Barbara's been running this measuring station out here. Not that they're going to put a nuclear power plant out there, of course, but this is just a model to study the effects of a basin where you actually have earthquakes. That's an easy place to make the study. But one of the things is that they have a bunch of seismic sensors there, and they put them all the way from here right on the surface all the way down into bedrock, which is 500 meters below. Well, that sensor that Jamie Stile, my colleague up there, runs is very useful for me because I want to help locate those earthquakes that we get in ANZUS. So we start collaborating. We can share data. I can access the data, use it as part of our network operations. He can give me the data. He gets it now through us all the way on his desktop instead of having to drive from Santa Barbara down to Borrego Springs and back to get it. So it's really been an advantage to him to start partnering up with us and leveraging these new generation technologies. He also did the same thing up at the Garner Valley Shake Table. We have a shake table facility here at Scripps, or not at Scripps, but it's at UCSD that's being installed at Camp Elliott on the far side of Interstate 15 at Pomerado Road through the School of Engineering. This is another facility that's very similar, which is basically they put sensors on it and they let the ground shake, and they want to see how these structures respond to earthquakes that occur. And one of the things that this area is so good about is that there are earthquakes up there. I mean, we have 2s, 3s, and 4 earthquakes occurring throughout this region on a yearly basis. So, I mean, 2s occur on a weekly basis, for instance. And then you want to see how these structures respond. Is it the same thing for a 2? Is it you just multiply it by 10 to get up to a magnitude 3, or does it respond in some different form or nonlinear response? And the other thing we can do, as mentioned earlier, is we can put out portable stations. Here's an example of a portable station, solar panel to power the system. We have the antennas up here and the data loggers down here. And just for an example of what types of things we're talking about, I mean, this is one type of sensor out there. This is something that will measure very strong ground motion. And we put these all over at every one of our sites now. This will measure up accelerations up to 2G, or twice gravity. So if we actually have enough acceleration to leave the ground, as long as it's bolted to the ground, it'll stay on it, and we'll be able to measure it. And then we have data loggers, these things like this orange box here, which are basically collect the data, digitize, and send the data out over the internet. We have these other sensors here, these Swiss sensors here, which are very high precision and measure earthquakes at all distance ranges from all the way from local events, which will occur from maybe 5-10 kilometers away, to something that's 10,000 kilometers away that might have, like the earthquake in Japan yesterday. This type of sensor will record very well, and we make some very nice recordings of it. And I think you'll be able to see some of that on the displays in the back if they're still up right now, so after this is over. And then one other thing that's become really important over the years is that, I mean, before, when we started doing this thing, every group had their own little set of stations that they worked. But these problems are getting bigger and bigger. The number of sensors that you can deploy and start analyzing gets more and more. Not everybody can deploy thousands of sensors, so why not collaborate and leverage each other's work? And so now we actually have data exchanges between Caltech and UCSD, Berkeley and San Diego, University of Nevada, Reno, and UCSD. And then we send data to Indiana University to be used in various high school education outreach programs, and we send it to the Iowa State Management Center for people to access the data worldwide. I mean, all the data that we collect is available in real time to anybody who wants it to analyze. So that's one of the things that's really, really been a big change in the way science is done. Instead of having one scientist work in their own little data set, now it's much more collaborative, both on the data exchange and also in the way that people work together analyzing data. So how do we go about locating earthquakes? This is one of the sort of basic issues we do and have to do. The first thing about, just like real estate, it's location, location, location. You can't do anything until you get location. So here's an example of an earthquake here, a small earthquake, and they're listed by the station that was closest to the earthquake to the station that's furthest from the earthquake. So the first station here is K and W, which I guess I forgot the labels on this side, but I can tell you that that's K and W. This one here is RDM. This one here is CRY, and then just by those three things alone, you pretty much know it's one of these earthquakes right there. It's the closest ones to those earthquakes, and it moves down further away. So what we measure is the first arrival of these events, and then call that a primary wave or compressional wave. And then you see a second wave coming in here, which is called a shear wave or a S wave. And that gives a different type of motion. And then when they get the display finished in here, you can actually go demonstrate that back on the earthquake display that they're putting together now. And the other thing we do is we organize these things so we have each different station has an individual trace here, organized from closest to furthest, so it comes in first, second, third, all the way down to the last. Time is across the bottom, so that's the time axis here. And then the other thing that people are very familiar with, as a concept of at least, is a magnitude. And so that's basically based on the amplitude, how big the excursion is at the measurement as at each individual site. So once you have the location, then we can calculate a magnitude. And once we have those two things, we can start building a catalog. And once you have that, you can start doing science. So that's sort of the order that you have to, the foundation that you have to go through to get to real research work. Well, and then you show those nice figures in the before, but what really happens is you have a guy, this is one of our former undergraduates used to work in our program, and this is how he really locates it. He stares at computer screens for a long time, and he gets to play with data, and he gets cross-eyed, and you have to boot him out of there after a while, and come back and keep locating earthquakes. So, but this is one of those, we always have 3 or 4 undergraduates working on data sets all the time, plus permanent analysts who are on permanent staff. So this is an example of what we see on a normal day at the office. This is what we hope to see on a normal day at the office until a few minutes from here. But on Halloween 2001, some of you probably were around and felt a little earthquake. Well, this is exactly what it looked like. So nice and quiet. This is what I hope I'm seeing back there on the screens over there. Which, yeah, it's okay. But you kind of walk along and kind of say, okay, well, time to go home, because this, it's late at night here, and say, don't need to work anymore. And then all of a sudden you start going, uh-oh, it all lights up. And so this is exactly what you would have seen if you were watching at that particular time. This is a replay of the data we recorded. It's like, I don't like seeing solid yellow displays. That's just not a good thing to see, particularly when it's close to you. But there's some interesting things that you can show on this thing. It's like you've got here, we've obviously organized this from the closest station, the furthest from top to bottom. So it hits here first and comes down further and further away. Well, you also notice that, okay, the little glyphs here, the P phases and things like that are part of the location code. So something that goes on, we have processes that automatically tell us where it occurred, a first estimate of where it occurred and how big it is. So that's when these P flags come up, we know that there's an earthquake that's happened there. But you look down here and say, okay, this is Toro Peak, and down here is San Diego. But look, there's a significant time lapse between the time it started up here and getting all the way back down here. And furthermore, this is at Thornton Hospital, it's stationed out here. Furthermore, the biggest shaking occurs even later. It's on that shear phase. That's where most of the damage occurs in structures. It's that second phase. It's not the first one, it's the second one. First one moves you up and down, second one moves you horizontally. And there you can, if you've been around earthquakes, it's like thunder and lightning. You just start counting 1001, 1002, multiply times 8, and it's 8 kilometers for every second of distance between the two. So, and then back in here, you finally start seeing the aftershocks kick in here. So how these are a bunch of little aftershocks starting fairly close to the main shock itself. So this is the kind of thing that you say, okay, we actually looked at this problem and set up kind of a prototype early warning system. And so using this same type thing, we know the earthquake's way up here. It's 60 miles here to San Diego, or 100 kilometers. It's right underneath one of our stations, so you know right away that at the station itself, it's shaking hard. The people up there really knew it. We knew it down here. You could feel it because you kind of rocked back and forth. People up there got tossed out of bed sort of thing. So it's a different scale up here. So you know something big shaking here, and all of a sudden these seismic waves are propagating out as closer and closer. So again, start here, work our way down to the coast. Well, the P wave times, you can see these things propagating out, and see the P wave comes out here, and it tends to see this one is like, that one must be, so it's 5 seconds, 10 seconds, 15 seconds, 20 seconds propagation out there. S waves travel slower, so it's much tighter contours, but the same thing, the waves propagate out and hit the coast at some later time. And so what we were actually able to do is that the earthquake occurred at this specific time. Well, one of the delays you always have is that it takes some time, the earthquake might occur, but you don't know it on the surface until the shock wave actually comes through the ground, gets to the surface. So there's some delay right there. If this earthquake happened to occur 15 kilometers deep, so it was 5 seconds, it was, 3 seconds before we actually knew that the first station started observing it. So you have a delay in here. So we waited till it was observed at about 5 stations, and we sent out an alarm. We didn't know the location exactly, but we knew there was heavy shaking going on in the region. And so here at Monument Peak, which is right here, we actually got the alarm out before the first wave phase hit it by a couple seconds. But down in San Diego at Mount Soledad, we actually beat it by about 10 seconds. And the heavy shake we beat by about 30. So this is the kind of things that you can start thinking about, ways that some technologies might be applied in an emergency response situation. Now this stuff isn't being done right now. These are the capability that we're testing and prototyping, but there's lots of issues of false alarms, how do you deal with these kind of things. So it's a tricky subject. And we work in, and they look in the details. You saw some of the aftershocks there I showed you on the real-time display. We're going to focus in on this little box here. The star is where the earthquake occurred. The green triangles are where the stations occurred, and the lines here are where the fault lines are. So here is the main aftershock sequence, and all of a sudden, Debbie Kilb and I were looking at this, and we kind of go, there's something very interesting about this data set here. It's like, gosh, look at this X right here. There's a place here there's almost no earthquakes. There's a place here there's almost no earthquakes. We don't know the answer to this yet. I mean, I'm showing you something that we're doing active research trying to understand this sort of phenomenon, but this is something that actually popped out of this. And it also turns out that this is essentially on track with the same, where the fault orientation of the earthquake that actually broke the first one. So we're trying to understand whether this is actually something, a stress relief, a release mechanism, and where the aftershocks are being controlled by the mechanism of the earthquake, the actual where the earthquake occurred. So one of the things we've done is partition it up into each quadrant to see if that would help solve the problem and see if we can move these earthquakes and make a more even distribution. But we haven't done it yet, so we're still bashing away on this data set, and I'll be very interested to find out in the next year or so what our real answer is for why we might see such a phenomenon. Oh, I wanted to go there. All right, now here's where it gets real fun. We're going to stop here. We're going to go to End Show, and we are going to go to there. So one of the types of things that we also do is that we actually started using visualization tools on these data sets. And so Debbie and others have put together a data set here, and I'm going to attempt to fly this system here. We got all sorts of earthquakes here. We have maps and the seismicity and the faults. And we can zoom it in here, and we start zooming in. We start seeing exactly what's going on in these different systems here. And go down. And so you can start seeing how the structure of these things work, of all these earthquakes. And I definitely want to do this. Turn off topo. So that's what the earthquakes look like underneath the ground while they're laid out in space. And let's see, we want to turn off the interlines. All right, so you can actually look at this thing, and then you can sort of rotate it around. And it looks like a nice star field or something like that. But this is the distribution of the earthquakes. And one of the things we're trying to understand is why we have this particular distribution of earthquakes. You can rotate it around in this direction. And when you get into a certain angle, which is coming up right about there, that's the best alignment that we can get along the fault. But what do you notice? It's not a line. We're getting a region where there's earthquakes occurring all through here, but it's not one specific line. It's not perfectly lining up on the trace. So this is another area of like, what is going on these faults that causes this distribution of earthquakes to occur in the region? Why do we not see it? And are these earthquakes occurring off of that? I mean, we're still waiting to see what might happen and trying to understand what the trigger mechanisms are for the larger earthquakes, and we don't know those answers yet. So this is a type of problem that we're trying to deal with in seismology right now. And let's see, let's go back to there. So, who was here on June 15th, 2004? Anybody? Everybody? How many of you felt this earthquake? I did too. Fortunately, it was in the middle of the day this time, so I didn't have to go to work. I was already there. So here's what the seismograms looked at here. As Mount Soledad is the upper trace. This is a measurement made at Thornton Hospital. This was made at San Clemente Island, and this is made out at Camp Elliott out there where those shake tables are at 15 and Palmyra Road. This is at Mission Trails Regional Park. Some of you may have seen the displays we do there. We set up data exchange with them. We actually have a seismic station at their place and bring in data. And this is a site that's up in Ramona. Well, this is one of those things where early warning systems don't work. Look at this. The first station that we recorded was Mount Soledad. It's already in this urban area. So unless we had a seismometer sitting out there on the seafloor, we could not have done that early warning. So it's one of those situations that, depending on where the earthquakes occur in California, it's going to be a question of how these type of systems work. And so one of those issues that we have to think about when we where the coverage are. And actually, this is these faults out here do present some hazard to San Diego. So now getting back to the San Andreas fault system, and this is looks at the whole fault system here as a topography map of California, plus the offshore bathymetry that you see, the sea floor. And this is a kind of just a short history of the earthquakes that occurred through in 50-year chunks. So this is 1800, 1850. There's basically two significant earthquakes. Southern California, the 1812 Wrightwood one is one that actually knocked down missions and things like that. That's how we know what had happened. The interesting thing was that because it knocked down the missions and all the missions were along the coast here, that the original location was put in the offshore border region, right? Makes sense. I mean, missions here, here, and here are damaged. It should be out there. Well, it turned out later that someone got real smart and figured out through some tree ring dating that the earthquake actually occurred up on the San Andreas Fault up on the far side of the Cajon Pass there. So it's kind of a fascinating little study of the unreliability of just felt reports. As we get further along, 1850 to 1900, we've got quite a few more earthquakes, but what else is happening in that period of time? What goes up in California in that time window? Bingo, it goes up hugely. Gold rush, all these people come to California, they're felt. A lot more things are going to be felt. The big earthquake in this section here is the one that is most significant, is 1857 Fort Tejon earthquake. It's probably the largest earthquake. It's kind of a dead heat between that one and the 1906 San Francisco earthquake, which is the largest in California history. The next 50 years, say 1906 earthquake. There's other events of moderate size in Southern California and a couple others up in 1911 in Morgan Hill. And then we look at the last 54 years, and then we still have the 1989 Loma Prieta, but we still, nothing's as big as the Fort Tejon or 1906 earthquakes in any of this 50-year period. So what I'm going to show you now is some work done by Bridget Smith. She's getting ready to graduate, and this is part of her thesis work, and it's something that I found to be a very graphical way of showing how some of the earthquakes, how the California coast or state responds to earthquakes. So this color here is basically saying that this side is on the North American plate moving southbound and along this way, and that constant color means it's the same things. There's no change. Same thing with the yellow on this side. It means it's just going northbound. This side, that's where we are. We're headed to Alaska. These guys are headed down to Mexico, sort of thing. So that, but also what's occurring here. This is an example of one of the earthquakes in here, and this is when the earthquake occurs. The earth deforms around the fault. And these models show, kind of the pattern, kind of a butterfly pattern, which we would sort of expect to see around an earthquake occurring, and that the amount of deformation, then you'll see it relax, and so you can get a sense of scale of how much motion per year is by the color bar up here on this side. And there'll be a timestamp on the bottom. What we're going to see is a movie starting in 1800 working through the present of what's been happening from what we know of the major historical earthquakes. So it starts moving along. All of a sudden we get to, there one lights up California, and you see the relaxation as the response to the earthquake takes some time to die away. And that's one of the interesting things about it shows. I mean, earthquake breaks the ground, but it doesn't just stop right there. It takes a while for the response to die away. And so we're about ready to come up on 1857. Coming up right there, that's kind of lights up everything there. And it got to be a pretty active time in response following that period of time. See lots of earthquakes in there. And coming up on 1906, that ought to make an impression. And coming up into the 60s. But as you can see, California's a pretty active place. I mean, it's been that way for as long as people have settled here. So When people ask, do you expect to have another earthquake, the answer is yes. The only problem is I can't tell you when. Unless it just happened and it's already, shock waves already coming here, right? All right. And then you can take that information and start looking at what the stress history is and kind of look at where things happen, where you expect an earthquake to happen. Oops, an earthquake happened and the stress got relieved. The colors here indicate areas of high stress, and it goes away. And there's a Fort Tahone earthquake coming up, and it reduces the stress there. But in the meantime, these places that don't break are slowly building up with time. So this is kind of looking at the stress region for the whole state of California. And that one filled in there, and then stress slowly builds up with time. As you go, a little bit in Palm Springs, relieved a little bit of stress. Carroll Valley. And so this is pretty much the level of, say, the areas of high stress are in the red and the low stress are in the purple here. But if we go back and look, where are we doing now? Gee, right before the 1856, before the 1857 rupture, we had a pretty high stress up in the Bay Area, high stress in here, high stress kind of below the border. How does that look to compare to today's, what the models show for today? Yeah. So anyway, this is kind of what the modeling results show. It's a very graphical way of showing how things are working together, and it's kind of the thing that the next generation of scientists will be combining these tools and developing better theoretical models to come up with more precise modeling techniques to come up with better representation of this. But this is kind of where the state of the art is today, and some of the things that we can do in the combination of the visualization tools, the computational tools, the geological mapping tools, and the seismology and data recording tools. So that's where I'm going to stop, and I'll open it up to questions. The question is what are the data sent to the supercomputer center for? Well, this data are sent down through the internet, so it goes to many computers. Among them are the supercomputer center. But the data are recorded on a computer. We run a bunch of detectors on it because all the data coming in real time, all the time at us. And so we want to see right away where an earthquake occurs. And those data are then identified when there's an earthquake and when there's not an earthquake, and then they're written to disk, and then at that point we can actually come in and do the data review like you saw the analysts do there, and then from there we'll start turning on some more sophisticated computer programs to analyze the actual waveforms themselves, look at the time series history, and start looking at some of the modeling type things that we can do with the data. So we're trying to actually look at how the earthquakes work and how the Earth responds to the earthquakes. The question is comment on the seismic history at Hartfield, and yes, it is a very interesting place, and people have made a lot of predictions about when earthquakes occurred. Of course, when they made the prediction, the earthquake came 10 years later, but small details. I mean, there's supposed to be a 22-year recurrence interval, and it occurred at 30 years, which has just happened actually earlier this summer. Hartfield does happen to be a place where we get a lot of magnitude 5 to 6 earthquakes. I mean, it's something that's one of the reasons it's one of the most instrumented places in the world for studying earthquakes. Many groups have spent a lot of time and effort studying there, particularly the USGS, and the National Science Foundation just funded a major program. Nigella was mentioning the US Array program, another complementary program on that EarthScope research thing is this San Andreas Fault Observatory at Depth, SAFOD, which is looking at drilling down in the ground and then looking at several kilometers to try and drill into the fault to actually look at the fault properties. Because there's a lot of interesting geophysics going on there, because it's right at the boundary where there's a lock zone and where it goes into what they call a creeping zone, a transition zone. The other place it turns out where that has just about as repetitive in earthquakes is Imperial Valley. The one right here, I mean, it was 1979, which, if you were here, you certainly felt. In 1940, 1920 something, 1900. I mean, it has a very repetitive earthquake sequence too, in about the same way. So you do find places on the planet, and in the San Andreas system, that have much more repetitive earthquakes. Then you look at those dates that you looked on the San Jacinto, where it's very jagged. It's not very predictable at all. Does the Japanese earthquake relate to the California earthquakes? In specific, no. In general, they are both part of the same tectonic system. They're just opposite sides of the same plate. So yes, they are related in a very general sense, but there's no specific causative action between the two. The question is, are there strong tremors being recorded here in San Diego like they are in the Pacific Northwest? And the answer is no, because they're looking at a specific subduction zone. We have not seen the same type of phenomenon here that's being observed up there right now. And there are some very interesting things going on the subduction zone up near Vancouver Island, up in southern Canada, but we're not seeing that.
After an initial earthquake, how do you determine what is a new earthquake as opposed to an aftershock?
Good question. There is no strict formalism for that answer. I mean, it's in general, you sort of look at, if it's within a certain region, like magnitude 6 earthquake, if it's within, say, 50 kilometers of that earthquake and it's within a year or two, you might call it an aftershock. But I mean, you look at what happened. I mean, there's some kickers in here, because like you look at the Landers earthquake in 1992, which occurred up here in the Mojave Desert. There were earthquakes that are quite clearly triggered all the way up into Oregon and Wyoming based on that. And so there's some causative effect in there that is not well understood yet. But so the concept of an aftershock is a very fuzzy thing, and I would use that term very loosely. I mean, it's the same thing. Was it a foreshock? Is it an aftershock? Right? I mean, which one's bigger? Things like that. Sometimes you see, a small earthquake followed by a big earthquake. Sometimes it's the other way around. Sometimes you see clusters of earthquakes about the same size occur in a region. We've seen all that stuff here in Southern California. So it's a very fuzzy concept. It just sort of used to explain that why you might see something occur at the same place and reasonably following after a larger earthquake. Do we deal with people who make observations in Baja California and the Sea of Cortez? We have some association with the groups in CECESE, and they do have instrumentation out there. We don't have an active real-time data exchange right now, for instance. We do have a proposal to go in and do some very detailed studies between the Baja California side through the Sea of Cortez and onto the Sonoran side to look at the structure. So there's a fair amount of scientific exchange, but less so on the real-time data side. The question is, can you hear an earthquake? And the answer is yes. And having heard multiple ones in various places around the world, that you can be very certain. But it usually sounds like a very deep explosion underground. And the only place I've ever had it happen is someplace like in the Imperial Valley in the 1979 earthquake, and the Aftershock Sequence there was one of those situations where we're sitting in a restaurant, you hear this boom, and you feel yourself go up and down like this, and all the patrons in the restaurants run out of the room except the seismologists, who start going 1001, 1002. And then all of a sudden we got shaking like this, and then that we knew it was 16 kilometers away, and then we decided to leave the room, right? But yes, you definitely can hear it, but it's usually kind of got to be really close to you and right underneath you. So it's not something that other people hear things where you hear stuff shaking on the, like buildings cracking or on big earthquakes or trees rustling, things like that. But that's just the surface stuff. But actually hearing the earthquake, you have to be pretty close to it itself.
But the ground doesn't shake, but this thing happens in clusters.
Yeah. I don't know what this is, because I mean, if it was an earthquake, we don't see earthquakes occurring under Mount Soledad. So then we do have instruments right on the mountain there. So.
How do you measure the stress you're showing on the maps here?
Oh, actually, let Bridget answer that one. Basically, these maps here are basically built on the fact that we have a model, a viscoelastic model of a plate of a certain thickness, of 30 kilometers was used for this particular model, and then kind of a low viscosity zone underneath it, and then when the things break. So the assumption was that the whole crust broke on these whole earthquakes, and so you can know that these sections are locked, and so they're building up. You know what the strain rate is across the fault, so it's basically 5 centimeters a year across the whole San Andreas Fault system. So down here we're partitioned between the San Andreas Faults, San Jacinto Fault, Elsinore Faults, and some of the offshore faults. Up further north, it's pretty much all taken up on the main fault up near Hartfield, things like that. So it's a calculation based on those parameters and what the physical parameters are of the crustal solid that you're using, of the plate. The question is do the explanatory models change with the advances in data collection? I think the models change much more based on the fact that we have much higher CPU power, more disk space, and more CPU cycles that we can use. And so usually those are mathematical calculations. We're spending a lot of effort now actually trying to do much more tying the improvement to the data quality to the models themselves and try and get more interaction between the two. But right now it's done, you collect your data, you build your models, and then do the comparisons between the two. And that's the kind of the standard mode at this point, although the direction's clearly tying all these things together and actually closer to real time. The question is whether animals can help predict earthquakes, and there are people who have spent careers studying that. I've never seen any credible work on that, and I have not worked on that myself, but I have literally been in a building in Central Asia, which is a 4-story building that was full of animals, top to bottom, where people went in and took measurements and recordings every few hours to see if there's any behavioral characteristic changes. But I've never seen anything published that would be, that was corroborated yet. So,
is there any evidence of fluid extraction or human activity of any sort influencing an earthquake?
Absolutely, yes. There are multiple places on the planet where fluid extraction, one example would be the Coalinga earthquake in 1982, 83, which was near the San Andreas, not on the San Andreas Fault, but a fault that was more inboard than that, but it was a magnitude 6 earthquake caused by that. There's other situations where you fill up a dam, and seismicity has kicked up and actually generates small to moderate earthquakes. It's never been a case where it's been a huge earthquake, but certainly ones that you might suspect up to the magnitude 6 level that could have some influence because of something that humans have done.
Great. Well, Frank, thank you very much. I'm sure you got